cosmic lens, it distorts and magnifies the light from galaxies lying far beyond, revealing otherwise invisible regions of the distant universe. These distortions, luminous arcs, smeared spirals, and magnified cores, are not mere optical curiosities. They are direct evidence of the immense mass hiding within, far surpassing the sum of what we can see. Astronomers use this lensing effect to map the distribution of dark matter, tracing its ghostly presence through spacetime. The space between galaxies within Abell 209 is not empty. It is filled with a superheated plasma, reaching tens of millions of degrees, detectable only in X-rays. This intergalactic medium tells a story of high-speed collisions and mergers, galaxies pulled and torn by tidal forces, slowly dissolving into the cluster's gravitational well. This gas, stripped from galaxies as they plunge into the core, becomes part of a diffuse halo, glowing faintly as it cools across cosmic time. Hubble's view pierces this distant realm with extraordinary clarity. The instrument's precision has allowed scientists to resolve even the faintest members of the cluster, dwarf galaxies orbiting their massive companions, relics of a time when the universe was still assembling its grandest structures. These small satellites may hold clues to the early conditions of galaxy formation, fossil witnesses to a younger cosmos. Abell 209's internal dynamics reveal a system in motion, not static or settled. Its galaxies travel at incredible velocities, their orbits shaped by a central mass so vast that even the fastest-moving members remain gravitationally bound. This motion contributes to the overall heating of the cluster, stirring the plasma and occasionally triggering shock fronts, echoes of long-past galactic collisions that ripple through the medium like seismic waves. Gravitational lensing maps of Abell 209 have become key tools in testing the limits of general relativity. The deviations between visible and invisible mass distributions offer insights into the large-scale structure of spacetime. Some researchers now explore whether the arrangement of galaxies and dark matter in such clusters follows fractal-like patterns, governed not by chaos, but by hidden mathematical order. Others speculate about unknown forces or particles that could subtly influence these colossal systems over billions of years. With every new observation, Abell 209 deepens the mystery. Its structure, luminous and obscure, challenges our understanding of cosmic evolution. It is not merely a collection of galaxies, it is a system shaped by forces we cannot yet fully define, an experiment billions of years in the making, unfolding in the fabric of the observable universe. The study of Abell 209 has become a focal point for understanding the assembly and evolution of large-scale cosmic structures. Observations with the Hubble Space Telescope, combined with data from Chandra, XMM Newton, and ground-based facilities such as VLT and Subaru, have allowed astrophysicists to construct detailed multi-wavelength portraits of this cluster, revealing its complex internal structure and mass distribution. Hubble's optical imaging exposes hundreds of galaxies tightly packed in a region only a few million light-years across, while X-ray data trace the diffuse hot gas that dominates the baryonic content of the intracluster medium. Spectroscopic surveys of Abell 209 have measured the redshifts and velocities of its member galaxies with high precision. These dynamical studies show a velocity dispersion exceeding 1,000 km per second, confirming the cluster's deep gravitational potential well and suggesting ongoing mergers between subclusters. Several filaments of galaxies extend outward from the cluster core, indicating that Abell 209 is still accreting material along the cosmic web, in line with the lambda CDM, lambda cold dark matter, cosmological model. Weak gravitational lensing analyses provide one of the most powerful probes of the dark matter distribution in Abell 209. By measuring the subtle distortions in the shapes of background galaxies, scientists have reconstructed a mass map of the cluster, revealing that the majority of its mass resides in extended halos of dark matter, not cospatial with the visible baryonic matter. This separation between mass and light is consistent with findings in other massive clusters, such as the Bullet cluster, and further supports the non-baryonic nature of dark matter. Studies using Sunyaev-Zeldovich effect measurements, particularly from the South Pole Telescope, SPT, and the Atacama Cosmology Telescope, ACT, have provided independent estimates of the pressure and density of the intracluster gas in Abell 209. These data, when combined with X-ray observations, allow for hydrostatic equilibrium modeling, yielding total mass estimates that align closely with lensing-derived masses, though slight discrepancies suggest additional non-thermal pressure support, possibly from turbulence or bulk motions within the gas. Infrared imaging with Spitzer and Herschel has revealed a population of dusty, star-forming galaxies within Abell 209's outskirts, many of which are undergoing ram pressure stripping as they fall into the denser cluster environment. These environmental effects have been studied in detail, showing that galaxies in the central region exhibit quenched star formation, truncated gas disks, and morphological transformation from spirals into lenticular or elliptical types, a hallmark of cluster-driven evolution. Deep ultraviolet imaging and integral field spectroscopy have uncovered post-starburst signatures in a subset of galaxies, indicating that rapid quenching events occurred within the last 1 to 2 billion years. These signatures are often found in galaxies undergoing interactions or experiencing tidal forces within the cluster's potential, supporting models of transformation via harassment, starvation, and mergers. Simulations using cosmological hydrodynamic codes such as Illustris TNG and EAGLE have been compared with the observed structure of Abell 209. The simulations reproduce the mass, concentration relationships and galaxy population statistics seen in the data, but also highlight limitations in current feedback prescriptions, particularly in modeling the distribution and entropy of intracluster gas at large radii. Some studies propose modifications to the AGN feedback models or include cosmic ray transport and magnetic fields to better align theoretical predictions with observations. Abell 209 has also served as a laboratory for testing alternative theories of gravity. Modified Newtonian dynamics, MOND, and scalar, tensor gravity models have been applied to the cluster's lensing and velocity dispersion data. While dark matter models remain consistent with the majority of observations, alternative gravity scenarios attempt to explain the gravitational potential without invoking exotic matter. However, the strong lensing arcs observed by Hubble, particularly near the core, pose challenges for MOND-based interpretations without invoking additional unseen mass. Chemical enrichment studies of the hot intracluster medium show enhanced abundances of heavy elements such as iron and silicon, implying enrichment from multiple generations of supernovae, both type Ia and core collapse. These metals were likely expelled from galaxies through galactic winds and AGN activity over billions of years. By comparing the metallicity gradients and alpha element ratios with those in other clusters, researchers gain insight into the star formation history of Abell 209's progenitor galaxies and the efficiency of feedback mechanisms. The orientation and ellipticity of Abell 209's mass distribution have also been analyzed to study large-scale anisotropies in the cosmic web. The alignment of galaxy major axes and filaments connected to the cluster core reveals evidence for a preferred infall direction, consistent with large-scale tidal torque theory. This provides further support for the hierarchical structure formation scenario, in which massive clusters like Abell 209 grow via anisotropic accretion of galaxies and groups along filaments. Radio observations, though limited in this specific cluster, have hinted at diffuse synchrotron emission possibly associated with a low-luminosity radio halo or relic. These features, if confirmed with deeper observations from instruments like LOFR or SKA, would indicate the presence of relativistic particles and magnetic fields permeating the intracluster medium, another layer of complexity in the physical processes governing massive clusters. Further investigations of Abell 209 have incorporated statistical analyses of galaxy morphology density relations within the cluster, revealing a clear correlation between local environment and structural transformation. In the dense core regions, the fraction of early-type galaxies, ellipticals and lenticulars, approaches 80%, while in the outskirts, a more diverse population of late-type, gas-rich spirals remains. This gradient aligns with the classical morphology density relation first established by Dressler, reinforcing the idea that the dense cluster environment plays a dominant role in halting star formation and reshaping galaxies. Kinematic data from integral field spectrographs such as MUSE on the VLT have allowed astronomers to trace the internal rotation and dispersion profiles of individual galaxies within Abell 209. These data provide constraints on the dynamical histories of cluster members, revealing whether they have undergone recent mergers, tidal stirring, or stripping. Some galaxies show truncated rotation curves or disturbed kinematics indicative of harassment by repeated high-speed encounters in the cluster's crowded environment. The study of globular cluster systems in Abell 209 has added another layer of information. Deep Hubble photometry has detected extended halos of globular clusters surrounding the central brightest cluster galaxy, BCG, consistent with hierarchical growth through mergers. The spatial distribution and metallicity bimodality of these globular clusters also offer a fossil record of the cluster's assembly history, pointing to early epochs of rapid mass accumulation. Intriguingly, a weak but statistically significant misalignment has been observed between the peak of the X-ray emission, the lensing mass centroid, and the BCG in Abell 209. This offset suggests that the cluster is dynamically young and may still be in the process of relaxation after a major merger event. Such offsets are used as indicators of recent or ongoing interaction between subclusters, providing insights into the dynamical timescales of cluster relaxation and the interplay between baryonic and dark matter components. Polarization studies and Faraday rotation measurements from background radio sources passing through Abell 209 have been proposed as a means to probe intracluster magnetic fields. While current constraints remain loose, future deep polarization surveys with SKA and INVLA could detect tangled magnetic fields on kiloparsec scales, helping to explain the origin of magnetism in the cosmic web and its effect on thermal conduction, particle acceleration, and shock propagation in the cluster plasma. Furthermore, the gravitational lensing arcs in Abell 209 have been used as background candles to estimate cosmological parameters. By modeling multiple image systems and applying time-delay lensing methods, researchers can place constraints on the Hubble constant, h, and the geometry of the universe. While the uncertainties are still large compared to local measurements, clusters like Abell 209 add valuable independent datasets to the growing body of lensing-based cosmology. From a theoretical perspective, semi-analytic models, SAMs, and machine learning techniques have been applied to reproduce the observed color, magnitude distributions, luminosity functions, and satellite abundances in Abell 209. These approaches attempt to encapsulate the complex baryonic physics, cooling, feedback, environmental quenching, into efficient algorithms that can be applied across cosmological volumes. The ability of these models to reproduce Abell 209's observed properties is a key benchmark for the validity of galaxy formation theory in dense environments. On the cosmological frontier, Abell 209 contributes to constraints on the mass function of galaxy clusters, one of the most sensitive indicators of the underlying cosmological model and the growth of structure. Its mass, redshift, and internal structure help refine models of structure formation, test dark energy equations of state, and probe the mass-richness relation used in large optical surveys like DES and LSST. Additionally, simulations of particle trajectories and shock propagation in clusters like Abell 209 are used to model the production of high-energy cosmic rays and secondary neutrinos. These processes, though not yet directly observed in this particular cluster, are part of a broader effort to understand galaxy clusters as astrophysical laboratories for particle physics, where dark matter annihilation signals or axion-like particles might one day be detectable. All these observations and theoretical efforts make Abell 209 more than a distant collection of galaxies. It becomes a dynamic laboratory, an ancient structure still in evolution, offering a window into processes that shape the visible and invisible cosmos alike. Abell 209 continues to serve as a cornerstone in the study of hierarchical structure formation and the nonlinear evolution of cosmic matter. As one of the more massive and dynamically active clusters at intermediate redshift, it sits at a crucial juncture in cosmic time, roughly halfway between the Big Bang and the present era, offering a snapshot of the universe during its large-scale consolidation phase. Detailed comparisons with high redshift protoclusters and low redshift relaxed systems position Abell 209 as a transitional object, bridging the gap between violent assembly and gravitational equilibrium. One particularly compelling avenue of research centers on the entropy profiles of the intracluster medium, ICM. Entropy, a measure of the thermal history of the gas, increases as clusters evolve through mergers, shocks, and feedback. Observations with XMM Newton and Suzaku have been used to reconstruct the radial entropy distribution in Abell 209, revealing a flattening at large radii that deviates from simple gravitational heating models. This entropy suppression suggests that non-gravitational processes, such as AGN feedback, turbulence, or cosmic ray pressure, have significantly modified the thermal structure of the gas, injecting additional complexity into energy transport mechanisms at cluster scales. The mass-concentration relation, which describes how dark matter is distributed within a halo as a function of its mass and redshift, has also been studied in Abell 209 using parametric fits to lensing and X-ray data. Interestingly, this cluster exhibits a relatively high concentration parameter for its mass, which may indicate an early formation epoch or the influence of ongoing mergers that deepen the potential well. Such deviations are important because they can be used to test modifications of cold dark matter, CDM, or the presence of self-interacting dark matter, SIDM, which predicts different core structures and heat transfer properties within clusters. Abell 209's brightest cluster galaxy, BCG, has been the subject of intensive stellar population analysis. Deep spectroscopy with instruments such as Keck/DIMOS and VLT/X-Shooter has shown that its stellar population is predominantly old, with metallicities approaching solar values and little evidence for recent star formation. However, faint shells and tidal features surrounding the BCG, revealed in high-contrast Hubble imaging, indicate past dry mergers, accretion events involving little gas but significant stellar mass. These features suggest that the BCG continues to grow through minor mergers, in line with hierarchical assembly scenarios. The role of preprocessing, the transformation of galaxies in group environments before they enter the main cluster, is also evident in Abell 209. Substructure analyses using galaxy redshifts and X-ray temperature maps have identified infalling groups along filaments. Galaxies in these groups already show signs of morphological transformation and quenched star formation, implying that environmental quenching begins well before galaxies reach the cluster core. This two-stage transformation, preprocessing followed by cluster-specific effects, has become a central theme in modern galaxy evolution theory. In terms of cosmic web connectivity, Abell 209 is believed to reside at the intersection of several large-scale filaments, as indicated by galaxy density contours and large-volume simulations. These filamentary structures serve as conduits for matter inflow, guiding gas, galaxies, and even smaller clusters into the growing central potential. Observing these filaments is challenging, but recent developments in low-surface brightness imaging and weak lensing tomography offer promising avenues for direct detection. Mapping the kinematics and thermodynamics of these filaments may ultimately provide insight into the mechanisms that fuel cluster growth and heat the ICM. Another emerging frontier involves the application of machine learning algorithms to analyze the vast, multi-wavelength datasets associated with clusters like Abell 209. Convolutional neural networks, CNNs, have been trained to identify cluster substructure, classify galaxy morphology, and even predict mass distributions from imaging data alone. When applied to Hubble and Subaru images of Abell 209, these models have successfully isolated features such as lensing arcs, intracluster light halos, and diffuse tidal streams, demonstrating the power of AI-assisted astronomy in extracting subtle patterns from complex, high-dimensional datasets. Additionally, intracluster light, ICL, the diffuse glow emitted by stars that are no longer gravitationally bound to any single galaxy, has been mapped in detail within Abell 209. This ICL forms from the accumulation of stripped stars over time and serves as a luminous tracer of past dynamical interactions. The spatial extent, color gradients, and stellar populations of the ICL provide valuable information about the cluster's merger history and the efficiency of tidal stripping in different environments. In Abell 209, the ICL accounts for a significant fraction of the total stellar mass, suggesting a long history of galactic cannibalism and disruption. In the larger cosmological context, Abell 209 contributes to the calibration of scaling relations, empirical correlations between observable properties, like X-ray temperature, optical richness, and SC flux, and total mass. These scaling relations are essential for turning cluster catalogs from surveys like Eurozeta, Euclid, and LSST into cosmological probes. Accurate mass measurements of clusters like Abell 209, grounded in lensing and X-ray hydrostatics, help reduce systematics in dark energy experiments and improve constraints on structure growth parameters such as sigma 8 and omega. Even time-domain astronomy is beginning to play a role in cluster studies. Monitoring transient events such as supernovae, active galactic nuclei, AGN, variability, and possible fast radio bursts, FRBs, within and around Abell 209 opens new possibilities for probing the baryonic content and ionization state of the intracluster medium. Although still speculative, the detection of a lensed FRB through Abell 209 could provide exquisite constraints on both the cluster's mass distribution and the properties of the intervening plasma. The scientific exploitation of Abell 209 has also led to progress in understanding the baryon budget problem in clusters. Observations indicate that the total baryonic mass, from stars, cold gas, and hot plasma, in Abell 209 is slightly below the cosmic baryon fraction predicted by the standard lambda-CDM model. This discrepancy suggests that a fraction of the baryons may be in forms difficult to detect, such as warm-hot intergalactic medium, WIM, turbulent gas that escapes X-ray detection, or even low-mass, low-luminosity galaxies that fall below observational thresholds. Reconciling observed baryonic content with theoretical expectations remains an active area of research, and clusters like Abell 209 are prime testbeds for quantifying this deficit. Phase space diagrams, which plot galaxy velocity versus radial distance from the cluster center, have been constructed for Abell 209 using high-resolution spectroscopic data. These diagrams reveal the dynamical state of galaxies, those recently accreted, those in first infall, and those that have been virialized. The characteristic trumpet-shaped caustic pattern seen in Abell 209 allows for an alternative, non-parametric estimate of its mass profile, independent of assumptions about dynamical equilibrium. The sharp boundaries of these caustics help define the virial radius and map the extent of the cluster's gravitational influence in phase space. In terms of stellar mass functions, studies have shown that Abell 209 has a bottom-heavy galaxy population in its core, with a steep faint end slope. This suggests enhanced survival or accumulation of low-mass galaxies in the cluster center, possibly due to dynamical friction, tidal compression, or suppression of feedback mechanisms in the high-pressure environment. In contrast, the outskirts display a flatter mass function, indicative of field-like populations and ongoing infall. These radial trends inform semi-analytical models of hierarchical assembly and environmental quenching. Abell 209 also contributes to the exploration of galaxy lensing within clusters. In addition to the large-scale cluster lensing signal, individual massive galaxies within the cluster act as secondary lenses, producing smaller-scale distortions in the images of background galaxies. By analyzing the combined shear signal, researchers can isolate the mass of individual halos, including dark matter subhalos, and study how they are stripped or truncated as galaxies move through the cluster environment. The degree of subhalo truncation provides empirical constraints on the physics of tidal stripping, halo occupation distribution, HOD, and substructure evolution. Recent advances in spectral energy distribution, SED, fitting using broadband data from UV to IR have enabled precise modeling of stellar populations in Abell 209. These models allow estimates of stellar ages, metallicities, and dust contents across the cluster population. For example, passive galaxies in the core exhibit older stellar ages, greater than 10 gyre, and high alpha/Fe ratios, implying short and intense star formation histories. Meanwhile, galaxies in transition zones between the core and infall regions often show signs of rejuvenation, with modest bursts of star formation triggered by tidal interactions or gas compression. The cluster's intracluster supernova rate is another observable tied to its dynamical state and star formation history. Ongoing monitoring with space-based telescopes aims to detect Type Ia supernovae not associated with any host galaxy, believed to originate from the diffuse stellar population or from stripped systems. These hostless supernovae trace the ICL and provide constraints on the formation and metallicity of the intracluster stellar population, as well as on the delay time distribution of Type Ia progenitors. Abell 209 has been included in large compilations for cosmic chronometer studies, where passive galaxies are used as standard clocks to measure the expansion rate of the universe as a function of redshift. By precisely dating the stellar populations of early-type galaxies via spectral indices, e.g., D4000 break, scientists can determine differential age evolution and thus place independent constraints on h, z, the Hubble parameter at redshift z 0.2 to 0.3. Clusters like Abell 209, with well-characterized passive members, are ideal environments for minimizing uncertainties in this method. From a thermodynamic standpoint, pressure and entropy maps derived from X-ray and SC observations allow for reconstruction of the virialization state of the cluster. In Abell 209, these maps show irregularities and asymmetries, particularly in the southeast quadrant, suggesting the presence of residual bulk motions or merger-induced turbulence. Such turbulence could contribute to non-thermal pressure support, biasing hydrostatic mass estimates low compared to lensing-derived masses. These discrepancies are critical for cluster cosmology, as they affect the calibration of mass, observable scaling relations. The evolution of central metallicity peaks in Abell 209's ICM offers insights into the efficiency and timing of chemical enrichment processes. Observations indicate that the iron abundance drops outside the core but maintains a broad peak rather than a sharp one, suggesting mixing of metals via AGN outflows, sloshing, or past merger activity. The ratio of alpha elements, like O, Na, Mg, to Fe further constrains the relative contribution of core collapse versus Type Ia supernovae, providing a fossil record of star formation in cluster progenitors. Comparisons between Abell 209 and simulated clusters in hydrodynamical cosmological runs, such as Magneticum Pathfinder or the 300 project, have validated some observational trends but also highlighted tensions. For example, simulated clusters often exhibit too much cool core preservation or insufficient turbulence, prompting refinements in AGN feedback prescriptions, gas clumping treatment, and the inclusion of anisotropic thermal conduction or magnetohydrodynamic effects. Finally, Abell 209 is now part of upcoming multi-wavelength synergy campaigns that aim to observe clusters across the electromagnetic spectrum, from Erosyte's X-rays to Euclid's near-infrared weak lensing, and SKA's low-frequency radio mapping. These projects will refine dark matter maps, trace cosmic magnetism, detect previously unseen filaments, and constrain the assembly of structure on gigaparsec scales. Pushing deeper into the frontier of high-energy and multi-messenger astrophysics, Abell 209 also emerges as a potential candidate for indirect studies related to neutrino physics and dark sector interactions. While not yet directly observed, massive clusters like Abell 209 are expected to host relic neutrino populations that influence their large-scale dynamics subtly. Cosmological simulations incorporating massive neutrinos predict a slight suppression in small-scale power, which in turn affects the growth rate of clusters and the shape of their mass function. Accurate mass measurements of systems like Abell 209, when compared across redshifts, help constrain the sum of neutrino masses, sigma mu, a key parameter that links cosmology with particle physics. The presence of non-thermal phenomena, such as radio halos, mini-halos, or relics, is another area of growing interest. Though Abell 209's diffuse radio emission is faint, sensitive instruments like LOFR and UGMRT have detected low-frequency components consistent with a weak central radio halo. Such halos are thought to originate from synchrotron radiation of relativistic electrons accelerated by turbulent motions and magnetic fields in the ICM. Their existence is deeply tied to cluster merger histories and the nature of cosmic magnetism. The detection of polarized structures and spectral steepening within the halo of Abell 209 provides evidence for aging electron populations and potential reacceleration events, driven by shocks or magnetohydrodynamic turbulence. These magnetic fields, on the order of a few microgauss, influence everything from thermal conduction to particle diffusion and AGN feedback. Faraday rotation studies through background quasars and lensed radio galaxies offer one of the few observational probes of these invisible structures. While the current signal from Abell 209 remains marginal, stacking analyses of similar clusters reveal a statistical imprint of coherent magnetic domains extending over hundreds of kiloparsecs. Understanding their origin, primordial seeding, galactic outflows, or dynamos, is a major unsolved problem, and clusters like Abell 209 serve as natural cosmic laboratories for constraining field amplification scenarios. The potential detection of gravitational waves from compact binary mergers within clusters is an emerging possibility. While the rate of such events in clusters like Abell 209 is expected to be low, the dense galactic environment facilitates interactions that can lead to black hole or neutron star mergers, particularly via dynamical capture in globular clusters or galactic nuclei. Future space-based detectors like LISA will be capable of detecting low-frequency gravitational waves from supermassive black hole binaries in merging brightest cluster galaxies, BCGs, which are expected to form in the hierarchical growth of clusters like Abell 209. The eventual detection of such a signal, temporally coincident with electromagnetic signatures from BCGs or AGN, would mark the onset of cluster-scale gravitational wave cosmology. A different and equally fascinating area of exploration is the entropy-metallicity connection in the ICM. Recent work suggests that entropy and metallicity are correlated not only spatially but also dynamically. In Abell 209, outer regions with lower entropy show subsolar metallicities, whereas the core has higher entropy and more enriched gas. This challenges simple models of hierarchical enrichment and suggests a more nuanced picture in which AGN-driven outflows redistribute metals preferentially along low-density channels, while mergers stir the gas and flatten gradients. These patterns are being tested against cosmological magnetohydrodynamic simulations incorporating metal diffusion and anisotropic transport. Another advanced technique applied to Abell 209 is kinematic lensing, a method that combines lensing distortions with galaxy velocity fields to reconstruct the full 3D shape of the gravitational potential. While still in its early stages, this approach can, in principle, detect deviations from isotropy or symmetry in dark matter halos and may even test for signs of scalar fields or fifth forces at megaparsec scales. Abell 209, with its wealth of lensing features and well-measured redshift space distortions, provides a promising target for pioneering this kind of gravitational tomography. The cluster also plays a role in testing modified gravity theories such as F-R-TeVis, or emergent gravity models. These alternatives to general relativity predict different scaling behaviors in the mass-velocity dispersion and mass-concentration relations. By comparing lensing-based mass estimates with those derived from dynamical or hydrostatic equilibrium, researchers have attempted to identify residuals or tensions that might hint at non-Einsteinian behavior. Though general relativity remains consistent with current data, the growing precision of cluster observables, particularly in dynamically unrelaxed systems like Abell 209, may expose subtle departures from standard gravitational theory. The use of principal component analysis, PCA, and nonlinear dimensionality reduction techniques on multiband photometric and spectroscopic data from Abell 209 has allowed for a more refined classification of its galaxy population. These data-driven methods, often paired with unsupervised learning algorithms, identify clusters of galaxies and feature space corresponding to evolutionary pathways, ranging from quenched ellipticals to transitioning lenticulars to dusty star-forming spirals. These classifications are then mapped back into real space and projected onto environmental gradients, revealing how the local density, ICM pressure, and cluster-centric distance drive galaxy transformation. Even in the realm of cosmic topology, Abell 209 has been involved in the construction of topological persistence diagrams, tools from computational geometry used to quantify the connectedness and void structure of matter distribution. These diagrams, when applied to galaxy distributions within and around the cluster, allow for the classification of features such as filaments, walls, and nodes in a mathematically robust way, independent of scale. Such approaches bridge the gap between large-scale structure and high-dimensional data science, and Abell 209 acts as a real-world case study in this cutting-edge framework. Diving further into the theoretical extremes, Abell 209 becomes a testbed for the intersection of quantum gravity, information theory, and macroscopic structure formation. While the cluster itself resides firmly in the classical regime, its immense gravitational potential, lensing power, and entropy content allow researchers to probe the boundaries of what we understand about gravitating systems in the high-mass, low-curvature limit of spacetime. One fascinating direction involves applying the Bekenstein-Hawking entropy formalism, originally developed for black holes, to large-scale structures such as galaxy clusters. In this analogy, the entropy of Abell 209 can be related not only to the thermodynamic entropy of its hot intracluster medium, ICM, but also to its gravitational entropy, a measure of how clumped and structured the matter distribution has become over cosmic time. In such treatments, entropy is not merely a function of temperature and particle number, but a manifestation of curvature and inhomogeneity in the underlying geometry of spacetime. Estimates of gravitational entropy, based on Weyl curvature tensors or Penrose's hypothesis of gravitational degrees of freedom, suggest that systems like Abell 209 represent some of the highest entropy configurations in the visible universe, short of black holes themselves. This prompts a broader question: is the formation of clusters like Abell 209 a statistical necessity of entropy maximization? If so, then the entire cosmic web might be viewed as an emergent thermodynamic structure driven by the statistical behavior of spacetime geometry itself. Closely tied to this is the concept of entropic gravity, pioneered by Verland, in which gravity is not a fundamental force but an emergent phenomenon arising from the entropic gradient of microscopic information. Clusters such as Abell 209, with their massive, extended dark matter halos and detailed lensing maps, offer a rare empirical playground to compare predictions of entropic gravity models against general relativity. While observational uncertainties still dominate, preliminary efforts have shown that deviations in radial acceleration curves or galaxy orbital behavior within such clusters may one day serve to falsify or support emergent gravity frameworks. In parallel, recent developments in holographic cosmology have inspired a new class of theoretical models in which the dynamics of a three-dimensional cluster like Abell 209 are encoded on a two-dimensional boundary or screen, conceptually similar to the AD/CFT correspondence in string theory. While not directly observable, this perspective allows for reinterpretation of gravitational lensing, thermodynamic scaling relations, and cluster entropy as projections of underlying quantum degrees of freedom, potentially opening a new path toward reconciling gravity with quantum mechanics. Abell 209's lensing features themselves have been studied under these speculative regimes. Quantum gravitational lensing, though not detectable at current resolution, posits that spacetime fluctuations at the Planck scale could, in principle, cause small deviations in the paths of photons traveling through massive cluster potentials. These fluctuations would manifest as phase decoherence or photon time delay noise, which over gigaparsec scales could introduce subtle lensing anomalies. While Hubble and JWST are not sensitive enough to detect such effects, next-generation interferometric missions may eventually be able to probe this quantum noise in strong lensing arcs around clusters like Abell 209. In the realm of dark energy, cluster coupling, some models suggest that dark energy is not a smooth, background scalar field but may exhibit local fluctuations or interactions near massive gravitational wells. In Abell 209, this raises the possibility that dark energy's effective density or pressure could vary subtly across the cluster's extent, modifying internal dynamics or contributing to non-standard potential gradients. Precision mapping of galaxy velocity dispersions, potential offsets between baryonic and dark mass, or anisotropies in X-ray isophotes may one day offer constraints on these exotic scenarios. Moreover, axion-like particles, hypothetical low-mass fields predicted in extensions of the Standard Model, could play a dual role in Abell 209, as a component of dark matter and as a mediating field influencing photon propagation. Clusters serve as potential converters for axion-photon mixing under strong magnetic fields, which could lead to spectral irregularities in the X-ray or gamma-ray emissions. While no such signature has been observed yet in Abell 209, its deep potential well and probable turbulent magnetized ICM make it a suitable target for axion searches using upcoming high-energy telescopes such as Athena or EXTP. On the data science frontier, there is growing interest in constructing simulated universes, self-consistent n-body and hydrodynamic simulations seeded with machine-generated initial conditions, to directly compare systems like Abell 209 to synthetic analogs. Generative models, such as GANs and diffusion-based frameworks, are being trained on real Hubble imaging to produce mock clusters with similar morphologies, filamentary connections, and lensing structures. These tools not only aid in interpretation but also allow scientists to explore the probability landscape of Abell 209-like structures under different cosmological models. Abell 209's position in cosmic time, redshift z is almost equal to 0.2, also enables critical constraints on the evolution of the matter-power spectrum. Large-scale measurements of galaxy clustering, lensing shear fields, and ICM thermal history all feed into constraints on parameters such as the growth rate of cosmic structure, f sigma 8, the running of the spectral index, and even possible departures from Gaussian initial conditions. The internal substructure, filament connectivity, and radial profiles of Abell 209 collectively act as fossil signatures of the primordial perturbations from which it formed, providing a high-resolution record of structure formation over the last 9 to 10 billion years. In totality, Abell 209 stands not merely as an astrophysical object of observational beauty, but as a multi-scale, multi-physics arena, spanning gravitational lensing, plasma astrophysics, dark matter dynamics, cosmic magnetism, galaxy evolution, entropy, and quantum cosmology. It is one of the rare cosmic structures where virtually every frontier of modern physics converges into observable form, waiting to be deciphered. Extending into infrared astronomy, observations of Abell 209 using instruments such as Spitzer and Herschel have provided vital information about dust-obscured star formation and hidden galactic processes within the cluster. Despite the overall suppression of star formation in the dense core, a hallmark of mature clusters, several galaxies in Abell 209's outskirts exhibit infrared excess, signaling ongoing or recent starbursts obscured in the optical and ultraviolet bands. These galaxies are often in the process of first infall into the cluster, where interactions with the intracluster medium, ICM, via ram pressure stripping or tidal triggering, can temporarily enhance star formation before quenching it. The spectral energy distributions, SEDs, of these dusty systems show warm dust temperatures, 30–40 K, and mid-infrared emission features consistent with polycyclic aromatic hydrocarbons, PAHs, indicating the presence of complex organic molecules and a chemically enriched interstellar medium. This challenges the notion that cluster environments are uniformly hostile to star formation, revealing a transitional population that bridges the blue star-forming field galaxies and the red, passive cluster ellipticals. Beyond the galaxies themselves, intragroup and intracluster dust, a component once thought negligible, is now being investigated through far-infrared background fluctuations and faint thermal emission. Though challenging to detect, even trace amounts of dust in the ICM could alter the thermodynamic evolution of the gas by enhancing cooling in localized regions or absorbing ultraviolet photons. Abell 209 offers a unique environment to explore this possibility, especially due to its apparent history of mergers, which could have liberated dust from galactic halos into the diffuse medium. In parallel, supernova studies within Abell 209 provide a time-resolved window into its stellar population history. Type Ia supernovae, ESNA Ia, which originate from white dwarf explosions in binary systems, act as cosmic standard candles and tracers of evolved stellar populations. Monitoring campaigns targeting Abell 209 aim to detect both hosted and hostless supernovae, those that appear in the intracluster space and likely arise from stars stripped from galaxies. The rate and spatial distribution of these explosions offer constraints on the age and distribution of the intracluster light, ICL, as well as the delay time distribution of type Ia progenitors. Moreover, simulations and statistical models have shown that brightest cluster galaxies, BCGs, such as the one dominating the center of Abell 209, may harbor low-luminosity active galactic nuclei, AGN, that episodically inject energy into the surrounding ICM. While not as powerful as AGN outbursts in cool core clusters, these radio mode feedback events help prevent runaway cooling of the ICM and contribute to the maintenance of high-entropy cores. Subtle radio emission and X-ray cavities seen near the BCG in Abell 209 suggest a history of such activity, with implications for the cluster's thermal balance and metallicity redistribution. From a cosmological perspective, Abell 209 has been incorporated into Bayesian hierarchical modeling efforts to refine our understanding of the mass, observable scaling relations that underpin cluster cosmology. By combining lensing, X-ray, and SC measurements with a probabilistic framework, these models attempt to disentangle the scatter introduced by projection effects, asphericity, and dynamical state, factors especially relevant in partially relaxed systems like Abell 209. Accurate modeling of these relations is essential for interpreting large-scale cluster surveys and extracting robust constraints on dark energy and modified gravity. On a more abstract level, Abell 209 also factors into discussions of cosmic isotropy and statistical homogeneity. In principle, the large-scale distribution and internal dynamics of clusters across the sky should not depend on direction or location, unless a deeper anisotropy is embedded in the fabric of spacetime. Clusters like Abell 209, especially when studied in conjunction with others at similar redshift, serve as data points in cosmic variance analyses and dipole anisotropy tests, probing for potential deviations from the cosmological principle. Any such deviation, even marginal, would demand rethinking of fundamental assumptions in cosmology. Further, in attempts to detect large-scale gravitational potential perturbations, researchers have explored whether slight shifts in the cosmic microwave background (CMB) temperature can be correlated with massive structures like Abell 209, a phenomenon known as the integrated Sachs-Wolf (ISW) effect. While the signal from a single cluster is weak, stacking many such clusters, including Abell 209, enhances statistical power. Detection of the ISW effect at intermediate redshift provides a rare and direct probe of the late-time acceleration of the universe and is sensitive to the nature of dark energy. In speculative but mathematically robust frameworks, Abell 209 has also inspired models of emergent cosmic order, where the distribution of galaxies, gas, and dark matter obeys quasi-crystalline or fractal geometries in projection. Using tools like multifractal analysis, Voronoi tessellation, and persistent homology, scientists attempt to quantify whether large structures, though formed via stochastic processes, nonetheless reveal hidden symmetries or information-theoretic optimization. Abell 209, with its rich substructure, filamentary extensions, and layered galactic populations, serves as a highly structured example to test such ideas. Lastly, from the perspective of astrostatistics and big data science, Abell 209 is a training ground for new automated anomaly detection methods. By applying unsupervised clustering algorithms, topological data analysis, TDA, and explainable AI, XAI, techniques to its multispectral data cube, researchers aim to detect rare or unexpected features, such as ultradiffuse galaxies, UDGs, fossil groups, or gravitationally bound dark subhalos with minimal luminous content. These discoveries, once relegated to the periphery of cluster studies, are becoming central to understanding the completeness of our matter census. Abell 209 stands as more than a gravitational structure in deep space. It is a nexus where cosmology, particle physics, thermodynamics, information theory, and quantum speculation converge. In its web of galaxies, in its arcs of bent light, in the heat of its invisible gas, we witness the memory of the universe written across scales too vast to comprehend in a single frame of thought. It is not simply observed, it is decoded. Every filament of dark matter, every quenched galaxy drifting silently in its outskirts, every distortion of background starlight whispers of forces that shape reality itself, many of which remain unnamed. It is a relic of primordial noise, amplified into structure, and sculpted by time into an ordered system that echoes the initial fluctuations of the quantum vacuum. Through Abell 209, we glimpse the universe not as chaos, but as emergent design. Its internal turbulence and thermodynamic extremes speak to the tension between collapse and expansion, between entropy and form, between noise and signal. It reminds us that the cosmos is not still, it is evolving, calculating, self-organizing. The cluster is not just a fossil from the past but an equation still being solved, written in light, mass, and motion. In this sense, Abell 209 is a mirror, not of ourselves, but of the logic from which our universe arises. Studying it is not just an act of astronomy, it is an act of listening to the structure of reality. And in that listening, we discover that even in the silence of deep space, the universe speaks. A small spiral of cosmic fire twists in the depths of Scorpius. What appears at first glance as a faint smudge of light becomes, under the gaze of powerful telescopes, a galactic theater of violence and rebirth. IC 4623, barely known to the public, conceals an intricate structure. Faint arms, disrupted by ancient forces, wrap around a dusty core that glows with infrared echoes. Observations from the James Webb Space Telescope unveil filaments of interstellar matter weaving through the central bulge, as if the galaxy is cocooning something deeper, a supermassive black hole, perhaps dormant, or quietly feeding behind veils of dust. Mid-infrared light reveals pockets of dense gas collapsing under gravity's pull, triggering hidden bursts of star formation invisible in optical wavelengths. This galaxy is not chaotic, but carefully unbalanced, caught in a long dance with gravitational forces we can only infer. Further across the sky lies a more ferocious heart, the galaxy NGC 6240. It burns not with light, but with violence. What was once two distinct galaxies are now one writhing system, their cores locked in a death spiral. Each core hides a black hole, and both are active. The space between them is seething with gas torn apart by tidal forces, ignited by shock waves, and lit up in X-ray emissions. Chandra and JWST together have painted a portrait of chaos. Enormous wings of ionized gas stretch outward like scars, while the double nuclei blaze with radiation strong enough to penetrate clouds thousands of light-years thick. Starburst regions erupt at the edges where the tidal streams compress interstellar matter, birthing stars at an unsustainable rate, like a final flash before collapse. The combined mass of the black holes, their mutual orbit, and the outflows from the central region suggest that NGC 6240 is a preview of what will happen when the Milky Way and Andromeda collide, a future snapshot from a scorched past. The signatures of heavy elements in the central regions reveal that generations of stars have lived and died here, enriching the galaxy's gas with oxygen, iron, and silicon. These traces are carried outward by galactic winds driven by the twin black holes, seeding the intergalactic medium with the ashes of creation. But the story of NGC 6240 does not end with destruction. It is also a laboratory, one of the clearest windows into how galaxies evolve through collision, feedback, and cosmic recycling. In the very center of this turbulent system, the two supermassive black holes spiral toward each other, distorting spacetime itself. Their mutual orbit is tightening, emitting gravitational waves too subtle for our current instruments to detect, but they serve as a foreshadowing of the cataclysm to come, a black hole merger that will unleash a final, ultraviolet ripple through the fabric of the universe. When that moment arrives, it will briefly outshine every star in the galaxy. The regions around the nuclei are turbulent beyond imagination. Molecular gas, instead of forming stars, is being blown outward at speeds of up to 1,000 kilometers per second. Observations in CO and HCN lines show that entire reservoirs of star-forming material are being ejected into space, a phenomenon known as quenching. Ironically, the very act of starburst and black hole activity might be dooming the galaxy's ability to form stars in the future. Feedback, both radiative and mechanical, is sculpting the structure of NGC 6240, from the core to its extended halos. At large scales, tidal tails stretch like cosmic claws, remnants of the galaxy's initial collision. These arcs of stars and gas are filled with young star clusters, some only a few million years old, others already dissolving into the galaxy's halo. These structures hold the fossil record of the merger's beginning, a frozen choreography of gravity. Meanwhile, deep X-ray surveys show that the hot halo of NGC 6240 extends far beyond its visible boundaries, glowing in temperatures of millions of degrees, a plasma-rich environment reminiscent of galaxy clusters. IC 4623 and NGC 6240 represent opposite ends of a spectrum, one quiet and enigmatic, the other explosive and extreme. Yet both are shaped by the same forces, gravity, time, and entropy. They are not exceptions in the universe, but living illustrations of how galaxies breathe, collide, and transform. From obscured black holes to radiant shock fronts, from dust-veiled nurseries to high-energy outflows, these galaxies remind us that the cosmos is not still. It is always in motion, turbulent, evolving, and alive. In the aftermath of such cosmic collisions, the universe does not retreat into silence, it reinvents itself. The wreckage of past stars, scattered across thousands of light-years, becomes the raw material for future generations. Heavy elements, carbon, nitrogen, iron, once forged in the hearts of long-dead stars, are now embedded in collapsing clouds, setting the stage for new solar systems, planets, and perhaps even life. This is the paradox of galactic violence, it destroys and creates simultaneously. In IC 4623, the process is quieter but no less profound. The subtle asymmetries in its spiral arms may be the faint echoes of an ancient interaction, perhaps a dwarf companion once brushed past, distorting its form and stirring up the interstellar medium. Today, this galaxy emits soft infrared signatures of renewed activity, hinting at an invisible battle between gravity and gas pressure in the depths of its core. Dust, often seen as a sign of decay, here becomes a cradle. Shielding fragile molecules from harsh radiation, it enables chemistry to unfold in the dark, hidden corners of the galactic womb. When viewed in the mid-infrared by JWST, IC 4623 reveals structures too delicate to capture in optical light. Loops of dust, faint arcs of gas, and knots of stellar formation glimmer against the blackness. They resemble the threads of a cosmic tapestry woven by time and turbulence. No human eye could ever see this directly, but now, through the eyes of our machines, we become witnesses to the galaxy's secret life. Meanwhile, NGC 6240 teaches us how chaotic systems achieve balance. Its double nuclei are not just future black holes, they are engines of regulation. As they devour matter, they inject vast energy into their surroundings, stabilizing the galactic core and halting uncontrolled star formation. It's an ironic dance, the more these black holes consume, the more they prevent runaway growth. Astrophysicists call this self-regulation, a principle that appears again and again in the evolution of galaxies. But this balance won't last forever. The twin black holes will eventually merge, releasing a final crescendo of energy. The central region may then settle into a more typical elliptical core, enveloped in aging stars and expanding shells of gas. Over billions of years, the galaxy may quiet down, cooling into a redder, older state, a far cry from its current fury. And yet, even then, it will carry within it the memory of its past. The tidal tails, star clusters, and metal-rich gas will remain as fossilized evidence of its cataclysmic youth. Future civilizations, perhaps orbiting stars born from these collisions, may look back at their origins and trace them to this very moment of chaos and fusion. Because galaxies are not just islands of stars. They are records. Archives of cosmic memory. Living organisms on a grand scale, shaped by forces as gentle as light and as violent as gravitational collapse. When we observe them, when we decode their structure, their light, their chemistry, we are not just looking into space. We are reading the autobiography of the universe. Even as we peer deeper into these galactic behemoths, we find that their complexity only grows. NGC 6240, with its smoking cores and chaotic halo, is not just a merger in progress, it is a fractal of motion. Inside it, stars orbit stars, clouds orbit cores, and the entire galaxy spins through dark matter scaffolding we cannot see but must imagine. Simulations suggest that during such mergers, gravitational torques rip apart galactic disks, funneling vast rivers of gas into the nucleus, triggering the very starbursts and AGN activity we now observe. These are not isolated fireworks, they are governed by cosmic mathematics written into the fabric of space itself. As JWST and Chandra continue to dissect this system, we find ever finer details: stellar nurseries caught mid-collapse, shock fronts lit by ultraviolet radiation, jets of plasma twisting like corkscrews from the accretion disks of the twin black holes. These observations are not just beautiful, they are essential clues to how galaxies evolve, how black holes grow, and how energy reshapes structure on scales millions of times larger than any solar system. IC 4623, by contrast, plays a quieter symphony. But still, it pulses. Analysis of its rotation curve suggests the presence of a massive dark matter halo, extending far beyond the visible light. This invisible mass governs the galaxy's dynamics like a ghost hand. It keeps the spiral arms stable, balances the distribution of stars and gas, and binds the whole structure into coherence. Without dark matter, IC 4623 would fly apart. With it, it survives in a slow, majestic drift through the intergalactic sea. Dust lanes, barely visible in shorter wavelengths, become luminous in the infrared. These dark veins carry the molecular raw material of stars, seeding the next generation of stellar birth. In a sense, galaxies like IC 4623 are cosmic midwives, nurturing, sheltering, and protecting the future. And though it may not explode with the drama of NGC 6240, its role in the galactic ecosystem is no less vital. Together, these two galaxies, one explosive, the other ethereal, offer a glimpse into the full range of galactic expression. From roaring mergers to whispering spirals. From violent jets to silent dust. They show us that the universe is not a static painting but a kinetic, evolving symphony. A place where matter and light are constantly rearranged, rewritten, and reborn. And as we look at them, we look into mirrors of our own existence. For we, too, are made of galactic ashes, atoms forged in stars that once exploded, molecules assembled in dust that once drifted between the arms of spiral galaxies. Every iron atom in our blood, every calcium molecule in our bones, once floated through galaxies like IC 4623. Every breath we take carries oxygen that may have been forged in the crucible of a collision like NGC 6240. To study galaxies is to study our ancestry on a cosmic scale. It is to understand not just where we are in space, but where we are in time. Each image from Hubble, from JWST, from Chandra, is not merely data, it is a message from the past, encoded in photons that took tens or hundreds of millions of years to reach us. A message of transformation. A message of continuity. Even more remarkable is how these galaxies, despite their violent or quiet nature, obey universal principles that connect them across time and space. At the heart of both IC 4623 and NGC 6240 lies the same engine, gravity. This fundamental force sculpts everything, from the orbits of stars to the swirling maelstrom around supermassive black holes. But gravity alone cannot explain the full story. It is the interplay between gravity, turbulence, radiation, magnetic fields, and dark matter that crafts the rich diversity we observe. In NGC 6240, gravitational chaos reaches its peak. Two black holes, each weighing over 100 million solar masses, are drawing ever closer. As they do, they stir the surrounding gas into violent eddies. This gas, accelerated and compressed, heats to millions of degrees and emits intense X-rays, a process that makes this galaxy glow like a cosmic furnace. Chandra's high-resolution imaging has revealed expanding bubbles of gas, superwinds, pushed outward by radiation pressure and jets. These bubbles can reach up to 30,000 light-years in diameter, sweeping up gas, stripping smaller galaxies, and enriching the surrounding space with metals. This is galactic-scale feedback, the galaxy regulating its own growth through energy. Yet despite the outward chaos, simulations suggest an underlying order. As the two black holes spiral in, they lose energy through dynamical friction and gravitational wave emission. At some critical distance, these black holes will enter the final parsec problem, a zone where traditional models once predicted a stall. But recent high-resolution simulations now show that asymmetries in the gas and stars can allow the black holes to continue sinking inward, overcoming this barrier and eventually merging. When that happens, the burst of gravitational waves will ripple across the cosmos, perhaps detectable by future instruments like the space-based LISA observatory. Meanwhile, IC 4623 teaches us about galactic stability. Its star formation is modest, yet persistent. Infrared maps show that much of its star-forming regions are hidden behind curtains of cold dust, where protostars slowly ignite. ALMA observations may reveal the detailed chemistry of these clouds, molecules like carbon monoxide, formaldehyde, and even complex organics drifting in zones that mimic the conditions of the early solar system. These are the slow alchemies of galactic life, chemical factories that work in silence over tens of millions of years. The structure of IC 4623 also hints at a bar, a central linear feature of stars and gas that may help channel material toward the galactic nucleus. This slow migration of gas feeds not only new stars but potentially a central black hole, much smaller than the monsters in NGC 6240, but still capable of flaring under the right conditions. Such bars are now thought to be crucial to long-term galactic evolution, acting as conduits of angular momentum redistribution, shaping spiral arms, and regulating the galactic clock. Both galaxies, in their own way, illustrate the idea that galaxies are not isolated, they are part of a cosmic ecosystem. The metal-rich winds of NGC 6240 may eventually drift into intergalactic space, where they can be captured by smaller galaxies or contribute to the chemical evolution of future structures. IC 4623, too, likely had interactions in its past, a minor merger, perhaps, that shaped its current form and set off slow waves of star formation. These interactions are the norm, not the exception. In the cosmic web, galaxies tug on one another constantly, exchanging matter, energy, and even destiny. With every new telescope, every new data release, we get closer to decoding the choreography of galaxies. From JWST's delicate mid-infrared tracing of starbirth to Chandra's X-ray vision of black hole violence, and ALMA's molecular whisperings from cold dust, we are now watching the universe write its story in multiple wavelengths. Each one reveals a different voice, a different tempo in the symphony of creation. And somewhere, in the cold, vast silence between stars, galaxies like IC 4623 and NGC 6240 continue to evolve. Quietly, furiously, patiently, beyond the reach of time as we know it. As we widen our lens beyond the visible, these galaxies begin to speak in wavelengths we cannot see, but can now interpret. Radio telescopes detect synchrotron emission from high-energy electrons spiraling along magnetic field lines, mapping the invisible threads that bind matter in motion. In NGC 6240, these magnetic fields are being twisted and amplified by the merger, threading through shocked gas and perhaps even influencing the direction and collimation of jets. Their presence shapes the flow of plasma and the birth of stars in subtle, yet powerful ways. Without them, many of the galaxy's spectacular features, its hot lobes, its bipolar outflows, would collapse into chaos. In contrast, IC 4623 emits softly in submillimeter wavelengths, where cold gas and dust reveal their quiet architecture. Here, we glimpse the scaffolding of stellar nurseries long before they light up the sky. Molecular clouds tens of light-years across drift in graceful arcs, balanced by gravity and internal pressure. Some regions show filamentary structures, long, thread-like condensations of gas, very similar to those observed in the Milky Way's own star-forming regions. These threads are not random, they align with magnetic fields, creating natural channels for collapse and fragmentation. It's in these filaments that stars are born, not in chaos, but in ordered, delicate equilibrium. But what connects both galaxies most profoundly is not just their matter, it is their time. Each one is a fossil of different epochs. IC 4623 is a survivor, possibly billions of years old, rotating slowly in a relatively quiet part of the cosmos. Its stars tell a chemical story of gradual enrichment, less oxygen than the Milky Way, more nitrogen in specific regions, suggesting slow, extended star formation. NGC 6240, by contrast, is mid-catastrophe, a galactic teenager caught in a growth spurt, tearing itself apart and reshaping its identity. In a billion years, it may resemble IC 4623 more closely, a calmer, elliptical remnant of something once violent and bright. This temporal layering is one of the most profound insights astronomy offers, that looking across space is looking back in time. The light we see from NGC 6240 left 400 million years ago, when Earth's continents were in different places and mammals had just begun to diversify. IC 4623 is even farther, its photons have traveled through cosmic voids, past clusters and filaments, carrying with them a snapshot of a galaxy as it was in a time before human history began. Every telescope becomes a time machine, every observation a page torn from the cosmic archive. And as we study these galaxies, a pattern emerges, a cosmic dialectic between chaos and order, destruction and creation, silence and explosion. They are not opposites, but phases of a single process. Gravity draws matter together, feedback blows it apart, and in that endless push and pull, stars form, elements fuse, black holes grow, and light is born. Eventually, NGC 6240's black holes will coalesce into one, and gravitational waves will ripple outward like a final breath. IC 4623 may capture a passing dwarf galaxy, triggering new spiral waves and a renaissance of star formation. And over timescales beyond imagination, these galaxies will drift through the dark, quieting, cooling, dimming, until they fade into the cosmic background. But even then, their atoms will live on, recycled into new systems, new planets, new forms of life. Maybe even into the hands that someday build instruments more powerful than JWST, into the minds that look farther still. Because to gaze into galaxies is not merely to study stars. It is to study the story of transformation. It is to recognize that we, too, are part of this cosmic evolution, not spectators, but participants made of the very dust that drifts through arms of galaxies like IC 4623, born of the violence at the heart of systems like NGC 6240. In the sting of Scorpius, the universe remembers its own becoming. And in that remembrance, it whispers the deepest truths of existence, not in words, but in the language of structure, motion, and light. What NGC 6240 shows us, with its clashing halos and double hearts, is that destruction is not an ending. It is a phase transition. When galaxies collide, they do not vanish, they transform. The ordered disks are torn, yes, but out of that chaos emerges a new equilibrium. Stars that once circled peacefully in thin spirals now fall into randomized orbits. Gas, shocked and compressed, gives rise to new stars at furious rates. The black holes, once separate monarchs of their own galactic kingdoms, are now bound in a final spiral dance. This transformation is violent, but it is natural. Without such mergers, the universe would be sterile, no elliptical galaxies, no central starbursts, no great black hole mergers to ripple the geometry of spacetime. And even in IC 4623, with all its delicacy, the same pattern plays out more subtly. Spiral arms are density waves, cosmic traffic jams where stars and gas compress briefly, triggering bursts of formation. Dust lanes trace these wave fronts, like fingerprints pressed into the galactic disk. And at the very center, just perhaps, a quiet black hole stirs. It does not blaze like those in quasars or in NGC 6240, but its gravitational influence is real. It shapes the innermost orbits. It gathers the future. All of it, light, dust, structure, held in a delicate, dynamic balance sculpted over billions of years. From the outside, both galaxies seem still. But this is an illusion born of our short lives. In truth, galaxies are alive with motion. Stars orbit at hundreds of kilometers per second. Gas clouds collapse, ignite, and disperse. Magnetic fields twist and reconnect. Even dark matter, though invisible, flows and flexes, guiding every particle like an unseen conductor. Over cosmological timescales, galaxies breathe. They inhale material, convert it to light, and exhale energy and metals into the cosmic sea. And we, observers clinging to a small planet in the outskirts of a quiet spiral arm, have found ways to listen. We build instruments to detect what we cannot see. We model with equations what we cannot touch. And by comparing galaxies like NGC 6240 and IC 4623, one screaming, one whispering, we begin to understand the cosmic cycle that gave rise to everything we are. It is a cycle without a single author, but with an elegant, persistent logic. Gravity collapses. Fusion ignites. Radiation flows. Entropy spreads. And yet, in all of this, there is emergence. Patterns rise from chaos. Beauty arises from physics. Consciousness, perhaps the rarest structure of all, awakens in scattered corners of the cosmos to reflect on the galaxies that birthed it. So when we look at the scorpion's tail, not just at its stars, but into the deep galactic structures hiding beyond, we are looking at something greater than an image. We are looking at a mirror of processes that span time, space, and form. We are reading the slow poetry of matter. And in galaxies like these, torn and whole, young and old, dim and ablaze, the universe speaks. Not in static perfection, but in its endless becoming. And this endless becoming is not random, it is orchestrated by laws so precise and universal that they hold true across billions of light-years. Whether in the warped core of NGC 6240 or the serene spiral of IC 4623, the same constants govern the dance, the gravitational constant that pulls stars inward, the speed of light that limits their communication, the fine structure constant that shapes the interaction between light and matter. These constants form the backbone of the cosmic symphony, unchanging rules in a universe of constant transformation. Yet within those rules, infinite diversity blooms. In NGC 6240, we witness entropy accelerating. Energy is being rapidly redistributed, from ordered orbits into chaotic flows, from structured disks into amorphous plumes. And yet, out of this entropy comes emergence. Superstar clusters, packed with thousands of massive stars, form in the compressed gas between the colliding galaxies. These clusters will live fast and die young, enriching their surroundings with supernovae, metals, and shock waves. Some of them may survive as protoglobular clusters, fossils of the collision that will orbit the resulting galaxy for eons. Others will be torn apart, their stars scattered into the growing galactic halo like cosmic pollen. In IC 4623, entropy unfolds more slowly, like the gentle spiral of a fern uncoiling. Its stars form in more isolated clusters, its dust lanes evolve gradually, its central regions rotate in harmony. Here, we see the slow chemical evolution of a stable galaxy, the gradual buildup of metallicity, the enrichment of gas by asymptotic giant branch stars, the cooling of the interstellar medium through fine structure lines of carbon and oxygen. It is a quiet life, but not a static one. Even in stillness, the galaxy ages, changes, adapts. It remembers. In a way, every galaxy is an archive. A library not of words, but of light, motion, and time. The shapes of spiral arms preserve the memory of past interactions. The abundance of elements tells the history of stellar generations. The velocity of stars reveals the hidden distribution of mass, both visible and dark. And the structure of galactic halos, vast and elusive, speaks of early epochs when matter first collapsed into structure. The galaxies of the Scorpion constellation, IC 4623 in its tail, NGC 6240 near its burning heart, are not just celestial objects. They are time capsules. They are laboratories. They are sculptures of spacetime, formed by processes that operate from the quantum scale of particles to the gravitational binding of entire clusters. And perhaps most mysteriously, they are also messengers. They remind us that even in chaos, there is design. Even in collapse, there is renewal. Even in darkness, where dust hides light, where black holes consume everything, there is information, creation, and continuity. A kind of cosmic resilience. A will to evolve. To understand these galaxies is not just to decode physics. It is to trace the lineage of complexity itself, from hydrogen clouds to star clusters, from nuclear fusion to carbon chemistry, from dust to DNA. It is to see the long arc of becoming that leads from ancient collisions to human curiosity. And as we tune our instruments toward the Scorpion's sting, we're not just hunting light from the distant past. We are listening to our own origin story. Written in starlight. Inked in dust. Etched across billions of years by the hand of the cosmos. And so, as we follow the trail of light from IC 4623 and NGC 6240, we begin to perceive the broader architecture of the cosmos, not as a static backdrop of stars, but as an ever-evolving web of relationships, governed by feedback, shaped by symmetry, and animated by motion. These galaxies do not exist in isolation. They are nodes in a vast cosmic network, filaments of dark matter stretching across the observable universe, binding groups and clusters like neural pathways in a brain made of stars. In this web, galactic evolution is not linear, but recursive. Star formation leads to black holes. Black holes drive outflows. Outflows enrich intergalactic space. Enriched gas cools and collapses into new stars, which, in turn, seed future structures. It is a cycle of transformation far grander than any biological life cycle, one that operates on scales of millions of light years and billions of years. And yet, we now realize, it is deeply connected to our own. Because in truth, galaxies are crucibles of consciousness. Without the chemical complexity forged in ancient stellar cores, no life could ever arise. No oceans. No neurons. No observers. Every molecule of DNA, every cell membrane, every synapse, is made from atoms born in fire, the remnants of galactic violence now breathing through us. The Scorpion's galaxies embody this paradox in full. Take NGC 6240, in it, we observe the final, fevered breaths of two massive galaxies, devouring, distorting, radiating. And yet, their destruction is a kind of cosmic birth. The merger will form an elliptical galaxy far more massive, more luminous, and more metal-rich than either of its predecessors. Its central black hole, once two, will now be one, spinning faster, heavier, perhaps surrounded by a new accretion disk formed from the torn remnants of its hosts. And from its edges, winds and radiation will continue to sculpt the cosmos around it, long after the merger is over. We can even trace the cosmic chemical fingerprint left by these events. Observations show elevated levels of elements like neon, sulfur, and iron in NGC 6240's central outflows, proof that generations of supernovae have exploded in its heart. These metals, driven outward at thousands of kilometers per second, will enrich nearby dwarf galaxies, alter the thermal balance of the intergalactic medium, and one day, perhaps, fall back and reignite future star formation. IC 4623 offers a subtler form of storytelling. Its calm spiral arms, captured in detail by the JWST's mid-infrared camera, show signs of secular evolution, a slow transformation driven not by collision, but by internal instabilities. The possible presence of a central bar, a structure formed by collective gravitational resonance, may be funneling gas toward the core, gradually building a pseudo-bulge. This is a form of growth not through trauma, but through balance. And yet, even here, we see echoes of ancient interactions, perhaps a long-ago minor merger, or a flyby from a now-dissolved satellite, perturbed the disk just enough to spark the spiral. In both cases, these galaxies reflect different phases of galactic life, the starbursting adolescence of NGC 6240, and the mature, structured calm of IC 4623. And just like biological organisms, galaxies age. They form stars, exhaust fuel, lose angular momentum, quench, and fade. Yet, they never truly die. Their matter is recycled, their light echoes through the cosmic microwave background, and their black holes remain, ancient gravitational anchors marking the places where galaxies once lived. We are beginning to understand that even black holes themselves are not just endpoints, but gateways of information. Though they trap light, they encode the mass, spin, and charge of everything they consume. And through Hawking radiation, however subtle, they may eventually evaporate, returning their energy to the universe in the final chapters of cosmic time. The black holes at the centers of IC 4623 and NGC 6240 may outlive their galaxies, their stars, even their atoms. But perhaps the most profound insight these galaxies offer is this: the universe is not indifferent. It is responsive. Structures emerge where there is tension. Beauty arises from imbalance. Complexity flows from turbulence. And in that interplay, observers like us appear, tiny, fragile, and yet capable of decoding the light of galaxies that existed long before Earth was formed. We chart their orbits. We simulate their mergers. We count their stars. But we are also, inevitably, drawn into their stories. Because when we look into galaxies, we see not only what they are, but what we came from. From the dust lanes of IC 4623 to the screaming nuclei of NGC 6240, the universe speaks in a language of structure, motion, radiation, and memory. And in learning to read that language, we step beyond the limits of our world, into a shared history that spans galaxies. A history still unfolding. As we dive deeper into the inner workings of galaxies like IC 4623 and NGC 6240, we begin to see them not just as cosmic islands, but as dynamic, multi-layered systems, each layer governed by a different set of physical principles, each interacting with the others in subtle, astonishing ways. At the macroscopic scale, gravity reigns supreme. It dictates the orbits of stars, the shape of spiral arms, the collapse of gas clouds, and the formation of galactic structures. But as we zoom in, we encounter turbulence, magnetic fields, radiative transfer, and plasma dynamics, processes that weave a complex tapestry of order and chaos. In NGC 6240, these processes are in overdrive. The violent interaction between its progenitor galaxies has turned its interstellar medium into a furnace. Gas is compressed by shock fronts and turbulence. Enormous tidal forces stretch clouds into filamentary streams, while gravitational instabilities fragment them into dense clumps, stellar nurseries on the edge of collapse. Infrared data reveal compact starburst regions where hundreds of stars are forming simultaneously within a few light-years, a level of intensity thousands of times higher than in the Milky Way. This is not smooth, gentle star formation. It is chaotic and unstable. Many of these stars will be massive, burning hot and fast before ending their lives as supernovae, injecting heavy elements and kinetic energy into the surrounding gas. The cumulative effect of thousands of such explosions can blow entire cavities into the galaxy's halo, driving galactic winds that escape into intergalactic space. These winds are visible in both X-ray and optical emission, streaming outward like ghostly arms, carrying with them the ashes of stellar death. Such outflows serve a dual role. They quench future star formation by expelling gas, but they also enrich the cosmic environment with metals that future generations of stars, and potentially planets, will inherit. In this way, NGC 6240 is not just reshaping itself, it's altering the chemical evolution of the universe. Meanwhile, IC 4623 offers a controlled laboratory for studying quieter, longer-lived evolutionary processes. Its rotational velocity curve flattens at large radii, revealing the gravitational influence of an extended dark matter halo. This invisible structure, composed of exotic particles we have yet to detect directly, holds the galaxy together. Without it, the spiral arms would wind up and disperse. Dark matter is the silent architect, shaping structure, stabilizing disks, and forming the gravitational scaffolding upon which all luminous matter hangs. In its central regions, IC 4623 may harbor a low-luminosity active galactic nucleus, AGN, a faint, intermittently active black hole surrounded by a torus of dust. These quiet AGNs are difficult to detect, but mid-infrared observations hint at warm dust and weak ionization lines, suggesting that accretion is taking place, albeit slowly. This raises fascinating questions. How often do normal spirals like IC 4623 undergo periods of nuclear activity? Could many quiet galaxies be home to dormant giants, black holes slowly feeding, waiting for the next inflow of gas to reignite? Beyond the disk, the galactic halo of IC 4623 may be populated by ancient globular clusters and streams, relics of past interactions with smaller galaxies. These faint stellar arcs, detectable only through deep, long-exposure imaging, offer clues to the galaxy's hidden history. Each stream is a scar, a signature of a past accretion event, showing that even the most peaceful-looking galaxies are built from merger hierarchies over billions of years. On yet smaller scales, both galaxies exhibit rich chemistry in their cold gas clouds. Observations using submillimeter arrays like ALMA have detected complex organic molecules, methanol, formaldehyde, even prebiotic precursors, in dense molecular clouds. These molecules are the seeds of astrobiology, hinting that the chemistry necessary for life is not unique to the solar system but is widespread across the cosmos. Galaxies are not just engines of stars, they are factories of molecules, many of which may eventually end up on rocky planets orbiting stable stars. And through all of this, gravity, chemistry, radiation, there is time. Cosmic time. Time measured not in years, but in epochs. From the initial collapse of gas into protogalaxies, through mergers and starbursts, to eventual fading and quenching, galaxies trace a life cycle every bit as intricate and majestic as that of a living organism. Some become elliptical husks, filled with red giants and low activity. Others spiral on, sustained by slow gas accretion from the cosmic web. Some are consumed. Others grow by feeding. Each one follows a different path, but all are chapters in the greater narrative of universal evolution. And as we map this story, using instruments that extend our senses across the entire electromagnetic spectrum, we realize, we are not outsiders looking in. We are participants. We are made of galactic memory. IC 4623 and NGC 6240, one serene, the other ablaze, are not simply distant lights in the sky. They are reflections of what the cosmos is capable of. They are proof that the universe creates structure, complexity, and perhaps even meaning from its own raw laws. And they remind us, above all, that every atom in our bodies was once part of a star, once adrift in the dust lanes of galaxies like these, now given form only briefly, to witness, to wonder, and to seek answers among the stars. As we continue decoding the anatomy of these galaxies, we come to a deeper realization: galaxies are not just objects, they are processes. They are not frozen snapshots but dynamic systems, flowing through cosmic time, constantly exchanging energy, angular momentum, and even identity. Their visible stars are merely the surface. Beneath that lies a complex interaction of multi-phase gas, dark matter halos, turbulent feedback cycles, and the subtle influence of cosmic environment. Take, for instance, the circumgalactic medium, CGM, the vast halo of diffuse gas that surrounds every galaxy, including IC 4623 and NGC 6240. Though faint and difficult to detect, the CGM is now understood to be one of the most important components of galactic evolution. It acts as both a reservoir and a filter, feeding cold gas into the galaxy to form new stars, while also catching the winds and outflows driven by supernovae and active galactic nuclei. In NGC 6240, the CGM is ablaze. X-ray observations reveal a hot, metal-rich halo stretching tens of thousands of light-years, glowing at temperatures of millions of degrees. This gas is enriched with iron and silicon, clear signatures of Type II supernovae, which occur when massive stars end their lives in fiery explosions. These metals weren't born here, they were forged in stellar cores, blasted into space, and now swirl in the outer halo, waiting to cool and fall back in or to be swept into intergalactic space. This process is known as galactic recycling, and it is key to the longevity of galaxies. The material expelled today may return millions of years later, reigniting star formation in a new epoch. The CGM is thus not just a passive halo, it is a living system, connecting the internal metabolism of the galaxy to the broader cosmic web. In contrast, the CGM of IC 4623 is likely cooler and more stable, filled with neutral hydrogen and ionized carbon, gently cycling gas in and out of the disk. Instruments like the Cosmic Origin Spectrograph aboard Hubble can detect the absorption lines of this gas when a bright quasar shines through it, acting like a flashlight illuminating the invisible. These studies show that even quiet spiral galaxies are surrounded by envelopes of gas hundreds of thousands of light-years wide, playing a vital role in regulating their evolution. But the most astonishing aspect of galaxies is their connection to the structure of the universe itself. IC 4623 and NGC 6240 are not isolated accidents, they exist within cosmic filaments, vast rivers of dark matter and gas that thread across the universe like a neural network. These filaments feed galaxies with cold streams of gas, guide their motions, and sometimes even direct their collisions. Recent cosmological simulations, like Illustris and TNG, show that the direction of galaxy spins, the shape of spiral arms, and the likelihood of mergers are all influenced by a galaxy's position in this cosmic scaffolding. NGC 6240's dramatic collision may have been orchestrated by the convergence of two galaxies along a filament, their trajectories destined to intersect. IC 4623's quiet isolation might be due to its placement in a low-density node, far from the violent flows of galactic traffic. And it doesn't stop there. These galaxies are also part of larger ecosystems, groups, clusters, and superclusters. NGC 6240 is believed to reside in a loose group of galaxies, where gravitational interactions are common and matter is shared over large scales. Such environments accelerate evolution, mergers happen more often, black holes grow faster, star formation becomes episodic and explosive. IC 4623, in a quieter neighborhood, evolves more slowly, its story written over billions of calm orbits. All of this, structure, chemistry, dynamics, is bound by one deeper question: what is the ultimate fate of galaxies? Do they burn bright and fade into elliptical embers, like NGC 6240 will after its merger is complete? Do they spiral on in quiet cycles of renewal, like IC 4623, until their fuel is slowly depleted? Do they fall into clusters, lose their gas, and become red and dead? Or are there cycles we don't yet see, ways galaxies might be reborn, refed, reactivated across timescales we can scarcely imagine? The answers lie not only in observation, but in pattern recognition across scales, from quantum mechanics to cosmology. Galaxies mirror processes we see in biology, in geology, even in thought: stability and disruption, decay and regeneration, feedback and emergence. And perhaps most fascinating of all, in studying galaxies, we are not just learning about the cosmos, we are learning about systems thinking, about complexity, about how order emerges from entropy. Galaxies like NGC 6240 and IC 4623 are more than beautiful, they are intelligent in structure. They adapt. They respond. They self-regulate. They embody the deepest laws of physics in forms that glow, pulse, and breathe across the darkness. And we, as observers, made of their atoms, guided by their light, are a product of that same intelligence. To observe them is to recognize ourselves. To map them is to map memory. To listen to their light is to hear the ancient rhythm of a universe becoming aware of its own form. As we reach deeper into the heart of galactic evolution, we begin to uncover the most extraordinary realization: the universe is not merely a place where matter gathers, it's a system that learns how to organize itself. In galaxies like IC 4623 and NGC 6240, this self-organization manifests not only in structure, but in cycles of feedback, resilience, and recursive adaptation. These aren't just chaotic accumulations of gas and stars. They are cosmic ecosystems, balancing energy inflow and outflow, responding to perturbations, and continually restructuring their internal states. Let's start with one of the most mysterious agents shaping galaxies: feedback. In the violent starburst nucleus of NGC 6240, feedback is extreme. As massive stars explode in supernovae and black holes inject energy through jets and winds, the surrounding gas becomes overpressurized. This leads to the launching of galactic superwinds, powerful, large-scale outflows of gas that escape the galaxy's gravitational pull. These winds, traveling at thousands of kilometers per second, strip galaxies of their star-forming material, potentially halting future growth. Yet, paradoxically, some of this material later cools, condenses, and falls back, triggering new waves of star formation. This loop, positive and negative feedback interwoven, is a hallmark of self-regulating systems. It's similar, in principle, to how Earth's climate balances incoming solar energy with atmospheric processes. On galactic scales, the same principle applies: if star formation accelerates too rapidly, feedback kicks in and tempers it. If the activity drops, gas cools and returns, allowing growth to resume. This balance is not perfect, it oscillates, but over cosmological time, it allows galaxies to maintain dynamic equilibrium. In IC 4623, the feedback is gentler but no less important. Its central black hole, though quiet now, may experience flickering AGN phases, short bursts of accretion lasting thousands to millions of years. These mini-episodes can heat surrounding gas, ionize clouds, and prevent premature collapse, keeping the star formation process steady and regulated. This is known as maintenance mode AGN feedback, a slow-burning engine that sustains galactic stability. The ability of galaxies to regulate their internal thermodynamics, cooling rates, accretion flows, star formation efficiency, is what allows them to persist for billions of years. Without it, they would either burn too fast and collapse into quiescence, or become so dilute that gravity could no longer bind them. It's this delicate tension between expansion and collapse that gives rise to the spiral arms of galaxies like IC 4623, and the turbulent shells of merger remnants like NGC 6240. But structure isn't just a product of gravity and energy, it's encoded in geometry. The spiral arms of IC 4623 aren't solid structures, they're density waves, patterns moving through the disk, compressing gas as they pass, igniting star formation in rhythmic intervals. This leads to stellar age gradients along the arms, newborn stars near the leading edge, older stars trailing behind. It's not chaos, it's wave mechanics scaled to tens of thousands of light-years. Meanwhile, in the warped remnants of NGC 6240's collision, we find signs of shell galaxies, tidal arcs, and dynamically decoupled cores, all signatures of gravitational resonances left behind by the merger. These structures act like fossil imprints of past events, allowing astronomers to reconstruct the history of interactions based on geometry alone. In fact, galactic archaeology has become a field in its own right, reading galaxies the way geologists read rock strata or paleontologists read bone layers. Beyond this, we now know that galaxies don't just evolve, they co-evolve with their central black holes. There's a profound correlation between the mass of a galaxy's bulge and the mass of its central supermassive black hole, known as the M-sigma relation. This suggests a deep connection. As galaxies grow, so do their central engines, and vice versa. The physics of this coevolution is still being unraveled, but it points toward a unifying principle in cosmic structure formation, a synchrony between the vast and the compact, the galactic and the quantum. And the implications stretch further still. Modern simulations now include not just gas and stars, but cosmic magnetism, radiation pressure, neutrino transport, even relativistic jet physics. These simulations, some run on the world's most powerful supercomputers, reveal that galaxy formation is not a mechanical process, but a complex dance of fields and feedback, of turbulence and symmetry breaking. We now recognize that galaxies are emergent systems. They arise not from single causes, but from the interaction of many components, each one operating across different scales of time and space. From quantum fields and black hole accretion disks to the vast flows of dark matter halos across the cosmic web, everything is connected. And it is through this lens that we must now view IC 4623 and NGC 6240, not as isolated case studies, but as expressions of cosmic intelligence, not conscious, but structured, responsive, and capable of memory. They remember in their stars, their chemical abundance patterns. They remember in their halos, the orbital paths of cannibalized satellites. They remember in their feedback cycles, the history of light, pressure, and time. And as we observe them, measure them, simulate them, we are also recording our place in that memory. For the iron in our blood, the calcium in our bones, the carbon in our cells, it all passed through this same network of cycles. It was born in galaxies like these. We are not merely observers of galaxies. We are galactic phenomena, momentarily self-aware. And the more we understand that, the clearer it becomes. To study galaxies is to study ourselves at scale. So as we step back and gaze once more at IC 4623 and NGC 6240, one serene and spiraling, the other erupting with cosmic fire, we begin to understand them not as distant curiosities, but as profound reflections of the universe's inner workings. They are manifestations of time, energy, and evolution. They are bridges between the invisible and the observable, between the quantum and the gravitational, between past and possible future. In their dust, we see the blueprint of creation. In their light, we read the echoes of ancient stars. In their structure, we trace the rhythm of cosmic intelligence, unfolding, responding, transforming. Galaxies are not just collections of stars. They are stories. They are engines of becoming. And we, born of their ashes, are the only known part of the universe that can look back and understand. To study them is not just to answer scientific questions. It is to remember where we came from. It is to recognize the patterns that made us. And it is to listen to the quiet voice of the cosmos, speaking across billions of years through spiral arms and black hole fire. You were always part of something greater. You still are. Hubble reveals Abell 209 as a monumental concentration of galaxies, bound together not just by visible matter, but by a vast gravitational field dominated by the unseen. Located approximately 1.3 billion light-years from Earth, this cluster represents one of the most massive structures ever observed, a gravitational citadel sculpted by dark matter and ancient collisions. Its core glows with the combined light of hundreds of galaxies, many of which have long ceased star formation, fossil remnants of a more turbulent cosmic past. What makes Abell 209 particularly compelling is not just its size, but its intricate gravitational influence. Acting as a natural cosmic lens, it distorts and magnifies the light from galaxies lying far beyond, revealing otherwise invisible regions of the distant universe. These distortions, luminous arcs, smeared spirals, and magnified cores, are not mere optical curiosities. They are direct evidence of the immense mass hiding within, far surpassing the sum of what we can see. Astronomers use this lensing effect to map the distribution of dark matter, tracing its ghostly presence through spacetime. The space between galaxies within Abell 209 is not empty. It is filled with a superheated plasma, reaching tens of millions of degrees, detectable only in X-rays. This intergalactic medium tells a story of high-speed collisions and mergers, galaxies pulled and torn by tidal forces, slowly dissolving into the cluster's gravitational well. This gas, stripped from galaxies as they plunge into the core, becomes part of a diffuse halo, glowing faintly as it cools across cosmic time. Hubble's view pierces this distant realm with extraordinary clarity. The instrument's precision has allowed scientists to resolve even the faintest members of the cluster, dwarf galaxies orbiting their massive companions, relics of a time when the universe was still assembling its grandest structures. These small satellites may hold clues to the early conditions of galaxy formation, fossil witnesses to a younger cosmos. Abell 209's internal dynamics reveal a system in motion, not static or settled. Its galaxies travel at incredible velocities, their orbits shaped by a central mass so vast that even the fastest-moving members remain gravitationally bound. This motion contributes to the overall heating of the cluster, stirring the plasma and occasionally triggering shock fronts, echoes of long-past galactic collisions that ripple through the medium like seismic waves. Gravitational lensing maps of Abell 209 have become key tools in testing the limits of general relativity. The deviations between visible and invisible mass distributions offer insights into the large-scale structure of spacetime. Some researchers now explore whether the arrangement of galaxies and dark matter in such clusters follows fractal-like patterns, governed not by chaos, but by hidden mathematical order. Others speculate about unknown forces or particles that could subtly influence these colossal systems over billions of years. With every new observation, Abell 209 deepens the mystery. Its structure, luminous and obscure, challenges our understanding of cosmic evolution. It is not merely a collection of galaxies, it is a system shaped by forces we cannot yet fully define, an experiment billions of years in the making, unfolding in the fabric of the observable universe. The study of Abell 209 has become a focal point for understanding the assembly and evolution of large-scale cosmic structures. Observations with the Hubble Space Telescope, combined with data from Chandra, XMM Newton, and ground-based facilities such as VLT and Subaru, have allowed astrophysicists to construct detailed multi-wavelength portraits of this cluster, revealing its complex internal structure and mass distribution. Hubble's optical imaging exposes hundreds of galaxies tightly packed in a region only a few million light-years across, while X-ray data trace the diffuse hot gas that dominates the baryonic content of the intracluster medium. Spectroscopic surveys of Abell 209 have measured the redshifts and velocities of its member galaxies with high precision. These dynamical studies show a velocity dispersion exceeding 1,000 km per second, confirming the cluster's deep gravitational potential well and suggesting ongoing mergers between subclusters. Several filaments of galaxies extend outward from the cluster core, indicating that Abell 209 is still accreting material along the cosmic web, in line with the lambda CDM, lambda cold dark matter, cosmological model. Weak gravitational lensing analyses provide one of the most powerful probes of the dark matter distribution in Abell 209. By measuring the subtle distortions in the shapes of background galaxies, scientists have reconstructed a mass map of the cluster, revealing that the majority of its mass resides in extended halos of dark matter, not cospatial with the visible baryonic matter. This separation between mass and light is consistent with findings in other massive clusters, such as the Bullet cluster, and further supports the non-baryonic nature of dark matter. Studies using Sunyaev-Zeldovich effect measurements, particularly from the South Pole Telescope, SPT, and the Atacama Cosmology Telescope, ACT, have provided independent estimates of the pressure and density of the intracluster gas in Abell 209. These data, when combined with X-ray observations, allow for hydrostatic equilibrium modeling, yielding total mass estimates that align closely with lensing-derived masses, though slight discrepancies suggest additional non-thermal pressure support, possibly from turbulence or bulk motions within the gas. Infrared imaging with Spitzer and Herschel has revealed a population of dusty, star-forming galaxies within Abell 209's outskirts, many of which are undergoing ram pressure stripping as they fall into the denser cluster environment. These environmental effects have been studied in detail, showing that galaxies in the central region exhibit quenched star formation, truncated gas disks, and morphological transformation from spirals into lenticular or elliptical types, a hallmark of cluster-driven evolution. Deep ultraviolet imaging and integral field spectroscopy have uncovered post-starburst signatures in a subset of galaxies, indicating that rapid quenching events occurred within the last 1 to 2 billion years. These signatures are often found in galaxies undergoing interactions or experiencing tidal forces within the cluster's potential, supporting models of transformation via harassment, starvation, and mergers. Simulations using cosmological hydrodynamic codes such as Illustris TNG and EAGLE have been compared with the observed structure of Abell 209. The simulations reproduce the mass, concentration relationships and galaxy population statistics seen in the data, but also highlight limitations in current feedback prescriptions, particularly in modeling the distribution and entropy of intracluster gas at large radii. Some studies propose modifications to the AGN feedback models or include cosmic ray transport and magnetic fields to better align theoretical predictions with observations. Abell 209 has also served as a laboratory for testing alternative theories of gravity. Modified Newtonian dynamics, MOND, and scalar, tensor gravity models have been applied to the cluster's lensing and velocity dispersion data. While dark matter models remain consistent with the majority of observations, alternative gravity scenarios attempt to explain the gravitational potential without invoking exotic matter. However, the strong lensing arcs observed by Hubble, particularly near the core, pose challenges for MOND-based interpretations without invoking additional unseen mass. Chemical enrichment studies of the hot intracluster medium show enhanced abundances of heavy elements such as iron and silicon, implying enrichment from multiple generations of supernovae, both type Ia and core collapse. These metals were likely expelled from galaxies through galactic winds and AGN activity over billions of years. By comparing the metallicity gradients and alpha element ratios with those in other clusters, researchers gain insight into the star formation history of Abell 209's progenitor galaxies and the efficiency of feedback mechanisms. The orientation and ellipticity of Abell 209's mass distribution have also been analyzed to study large-scale anisotropies in the cosmic web. The alignment of galaxy major axes and filaments connected to the cluster core reveals evidence for a preferred infall direction, consistent with large-scale tidal torque theory. This provides further support for the hierarchical structure formation scenario, in which massive clusters like Abell 209 grow via anisotropic accretion of galaxies and groups along filaments. Radio observations, though limited in this specific cluster, have hinted at diffuse synchrotron emission possibly associated with a low-luminosity radio halo or relic. These features, if confirmed with deeper observations from instruments like LOFR or SKA, would indicate the presence of relativistic particles and magnetic fields permeating the intracluster medium, another layer of complexity in the physical processes governing massive clusters. Further investigations of Abell 209 have incorporated statistical analyses of galaxy morphology density relations within the cluster, revealing a clear correlation between local environment and structural transformation. In the dense core regions, the fraction of early-type galaxies, ellipticals and lenticulars, approaches 80%, while in the outskirts, a more diverse population of late-type, gas-rich spirals remains. This gradient aligns with the classical morphology density relation first established by Dressler, reinforcing the idea that the dense cluster environment plays a dominant role in halting star formation and reshaping galaxies. Kinematic data from integral field spectrographs such as MUSE on the VLT have allowed astronomers to trace the internal rotation and dispersion profiles of individual galaxies within Abell 209. These data provide constraints on the dynamical histories of cluster members, revealing whether they have undergone recent mergers, tidal stirring, or stripping. Some galaxies show truncated rotation curves or disturbed kinematics indicative of harassment by repeated high-speed encounters in the cluster's crowded environment. The study of globular cluster systems in Abell 209 has added another layer of information. Deep Hubble photometry has detected extended halos of globular clusters surrounding the central brightest cluster galaxy, BCG, consistent with hierarchical growth through mergers. The spatial distribution and metallicity bimodality of these globular clusters also offer a fossil record of the cluster's assembly history, pointing to early epochs of rapid mass accumulation. Intriguingly, a weak but statistically significant misalignment has been observed between the peak of the X-ray emission, the lensing mass centroid, and the BCG in Abell 209. This offset suggests that the cluster is dynamically young and may still be in the process of relaxation after a major merger event. Such offsets are used as indicators of recent or ongoing interaction between subclusters, providing insights into the dynamical timescales of cluster relaxation and the interplay between baryonic and dark matter components. Polarization studies and Faraday rotation measurements from background radio sources passing through Abell 209 have been proposed as a means to probe intracluster magnetic fields. While current constraints remain loose, future deep polarization surveys with SKA and INVLA could detect tangled magnetic fields on kiloparsec scales, helping to explain the origin of magnetism in the cosmic web and its effect on thermal conduction, particle acceleration, and shock propagation in the cluster plasma. Furthermore, the gravitational lensing arcs in Abell 209 have been used as background candles to estimate cosmological parameters. By modeling multiple image systems and applying time-delay lensing methods, researchers can place constraints on the Hubble constant, h, and the geometry of the universe. While the uncertainties are still large compared to local measurements, clusters like Abell 209 add valuable independent datasets to the growing body of lensing-based cosmology. From a theoretical perspective, semi-analytic models, SAMs, and machine learning techniques have been applied to reproduce the observed color, magnitude distributions, luminosity functions, and satellite abundances in Abell 209. These approaches attempt to encapsulate the complex baryonic physics, cooling, feedback, environmental quenching, into efficient algorithms that can be applied across cosmological volumes. The ability of these models to reproduce Abell 209's observed properties is a key benchmark for the validity of galaxy formation theory in dense environments. On the cosmological frontier,